In 1933, on the Mississippi River at New Orleans, a worker stood on a barge while the current tried to move the job out from under his feet. In front of him was not a bridge yet, not a steel span, not a railroad deck, not the great crossing that would later carry trains and cars high above the river. In front of him was mud, moving water, hanging cables, timber piles, stone, wire, and a circle that had to be built in the river before anything permanent could rise. The bridge they were trying to build would stretch about 22,995 feet for the railroad portion alone. Its main river span would reach 790 feet. Some of its main foundations had to go down to a layer of fine sand 160 to 170 feet below mean Gulf level. And the Mississippi current, depending on depth, could move up to 6 feet per second. That meant the first problem was not lifting steel. The first problem was holding still.
Before modern GPS-guided marine construction, before automated drilling systems, before computer models could show exactly how a riverbed might scour around a pier, the men building the Huey P. long bridge had to create stable ground where there was none. They had pile drivers, they had derricks, they had barges, they had willow mattresses, sheet piles, steel shells, concrete, and sand dredged from the river itself. And they had a river that could quietly erase the beginning of the bridge before the bridge even existed. The job began with a strange idea: if the Mississippi would not give them an island, they would build one. New Orleans had needed a crossing like this for decades. The city was one of the great port cities of the United States, but the port sat in a geography that turned movement into a daily fight. Rail freight on one side of the Mississippi often needed to reach lines on the other side. Instead of rolling straight across a bridge, cargo and rail traffic had to depend on ferries and transfers across a dangerous working river. That was slow. It was expensive. And on a river crowded with shipping, it was always vulnerable to weather, current, fog, and delay. A bridge sounded like the obvious answer, but on the lower Mississippi, obvious answers usually died in the mud. This was not a narrow creek where a crew could drop a few stone piers and build from bank to bank. This was the Mississippi at New Orleans, a deep, fast, commercial river that still had to remain open for navigation. The bridge could not sit low enough to choke river traffic. It could not use a simple line of easy piers. The War Department had to approve a clearance high enough for vessels, and the final design became a double-deck cantilever bridge built around a major navigation opening, with trains and roadway traffic carried on separate parts of the structure. That gave the engineers a second problem. If the bridge had to clear the river, the steel spans had to be large. If the spans were large, the piers had to take enormous loads. And if the piers had to take enormous loads, the foundations could not stop in the upper mud. That mud was the real enemy. In New Orleans, the ground near the river is not hard bedrock, waiting politely below the surface. It is a layered delta of clay, silt, sand, water, organic material, and old river deposits. Some layers can settle. Some can squeeze. Some can shift unevenly under weight. Around New Orleans, ordinary buildings often need piles because shallow soil can move enough to crack and tilt a foundation. For a bridge pier carrying railroad loads, highway loads, wind loads, river impact, and the weight of a huge steel truss, that kind of uncertainty was unacceptable. The engineers bored into the riverbed and sent the samples for analysis. Carl Terzaghi, one of the most important figures in the early science of soil mechanics, concluded that the main piers needed to reach a stratum of fine sand, about 160 to 170 feet below mean Gulf level. The piers had to pass through the higher clay layers, the sticky material locally called gumbo, because those layers could settle unevenly. Think about what that meant for the men on the river. They were not just building upward, they were building downward first. They had to make a foundation through a moving river, through soft and uncertain ground, to reach a deeper layer that could carry the bridge. And they had to do it in the early 1930s, with floating equipment, triangulation, pile hammers, winches, and men working close enough to the water that one wrong movement could put them in the current. The first visible piece of the solution did not look like a foundation, it looked like a giant mat.
Before a river pier could be sunk, the riverbed around it had to be protected from scour. Scour is what happens when moving water eats away the bed around an obstruction. Put a pier in a fast river, and the current does not simply slide past it. It accelerates around the object, digs at the bottom, and can remove the material that the pier depends on. For 5 of the piers, workers placed protective mattresses made from willow saplings, brush, and wire weaving. These were not bedding mattresses. They were huge riverbed armor. Men worked from barges, lowering the woven mats into the water and loading them with stones large enough to be handled by men. The stones pushed the mattresses down. The current pulled at them. The workers had to place them where the future foundations would stand, even though the bottom was hidden and the water was trying to drag the whole assembly away. For a man on one of those barges, the job was not a diagram. It was a wet deck under his boots, a stone in his hands, a line tightening somewhere behind him, and a foreman watching a mark the river kept trying to steal. He could not see the bottom. He could only see whether the mat, the barge, and the crew were still obeying the plan. 4 of the 5 mattresses landed within about 15 feet of their target. 1 did not. At Pier 1, the mattress missed badly enough that a second mattress had to be placed. That detail matters because it shows the real nature of the job. This was not a clean drawing becoming real by magic. This was a crew trying to put flexible brush, wire, and stone into a powerful river and make it stop in the correct place. Even before the concrete, before the caisson, before the steel, they were already fighting inches and feet in a place where the river measured everything in tons. And the mattress was only the skin. The builders still needed a body for the foundation.
The contractor for the main bridge substructure, Siemens-Helmers, used a method that sounds almost impossible the first time you hear it. They built sand islands in the Mississippi. The idea was not to construct the caisson directly from open water, with every operation at the mercy of current and floating equipment. Instead, workers would create a temporary artificial island at the pier site. They would surround it with a steel shell, fill it with sand dredged from the riverbed, and then build the caisson on top of that man-made ground. But to build the island, they first had to build a circle. Workers drove piles in radial bents through the protective mattresses and into the riverbed. A pile bent is a row or frame of driven piles that supports temporary work. Radial means those bents were arranged around the future pier like spokes or segments of a circle. From the waterline, it would have looked like men trying to draw geometry in a moving river with timber and iron. Every pile had to be driven down by a hammer, guided from floating equipment, and held in alignment while the current pushed on barges and gear. The pile driver did not gently place timber into the mud. It beat it down. The hammer rose. The pile head weighted. The hammer fell. The impact ran through the timber and into the riverbed. Again, again, again. The men around it had to manage lines, signals, braces, hoisting gear, and shifting footing while the pile disappeared into water and mud. A pile too far out of line could distort the false work. A bent without enough protection could later be exposed by scour. A barge pulled out of position could turn a controlled lift into a dangerous swing. Once the radial false work circle was ready, the crew could assemble the steel shell for the sand island. That shell was built from 10-foot-tall steel plate rings. The workers assembled 3 rings at a time on needle beams. Around the perimeter, 12 hoist frames took the weight and lowered the shell portion by winches. Then another set of rings was assembled above it. Bit by bit, the shell grew downward and upward around the future pier site. To the worker at a winch, this was not simply a steel shell. It was a hanging wall of plate, weight, and timing. If one side dropped too quickly, the ring could bind. If a signal was missed, men handling the next plate could be caught between moving steel and the frame. The island had to be built slowly because every fast movement gave the river another chance. This was temporary work, but it had to be built with permanent seriousness. If the shell failed, the sand would not stay. If the sand did not stay, the caisson would not have a stable platform. If the caisson did not sink correctly, the pier would not land where the bridge needed it. And if the pier did not land where the bridge needed it, the entire geometry of the crossing would begin to fight itself. After the rings were assembled, workers dredged the inside area and began filling the shell with sand from the riverbed. For the larger islands, the fill could reach up to 35,000 cubic yards. That number is easy to pass over, so slow it down. They were not spreading a small pad of fill. They were building a temporary island large enough to become a construction site in the Mississippi River. Every yard of sand had to be dredged, moved, placed, and held inside a steel boundary. The river wanted to move it. The weight wanted to settle. The bottom below, it was not a level concrete floor. And all of this was being done so the Real foundation could begin. Because the sand island was not the foundation. It was the table on which the foundation would be built. On top of that artificial island, workers began the caisson. A caisson is a large watertight foundation structure that can be sunk into the ground until it reaches a strong bearing layer. For the Huey P. long bridge, the caisson began with a steel cutting edge. Around it, workers built wooden forms, installed reinforcing, and placed jet nozzles and wells that would help control the sinking process. The first 20 feet of concrete were placed around the cutting edge. This gave the caisson enough mass and shape to start sinking evenly. Then came dredging. Material was removed from inside and below the caisson. As soil came out, gravity pulled the caisson down. When only about 2 feet remained above the sand island, workers added another 10-foot layer of concrete. Then they dredged again. The caisson sank again. Another layer was added. The process repeated. Build, dig, sink, check, build again. The bridge foundation was not lowered in one dramatic movement. It was persuaded downward, lift by lift, foot by foot, by the weight of its own concrete and the removal of soil beneath it. That sounded controlled, but it was never simple. The caisson had to stay plumb. If one side sank faster than the other, the structure could tilt. If the cutting edge met harder material on one side, it could hang up. If the excavation removed material unevenly, the whole mass could bind. Workers had to watch levels, alignment, dredging, jetting, and concrete placement while standing on a temporary island in a fast river. For the men on that island, progress did not look like a bridge rising into the sky. It looked like marks being checked, hoses and dredging lines being moved, concrete forms being reset, and another small drop in the caisson after hours of work. The bridge was still imaginary. The danger was not. It was under the platform, in the clay, in the water, and in the chance that one side would move before the other. And below them was gumbo clay. The word sounds almost harmless. It was not harmless. The higher clay layers were exactly what the engineers wanted to bypass. When the caisson reached the last portion of sinking, the excavation broke through this gumbo. The clay did not behave like loose sand that could be washed away evenly. It fractured into big pieces when excavated. Imagine trying to sink a massive concrete box through material that breaks out in chunks. Too much removed from one side, and the caisson can shift. Too little removed, and it can hang. A chunk jammed in the wrong place can disturb the movement. Everything about the operation is heavy, slow, wet, and unforgiving. Once 135 feet of caisson had been assembled above the cutting edge, the workers paused dredging and added a temporary cofferdam 50 feet tall. A cofferdam is a temporary barrier that lets crews isolate part of the work from surrounding water. In this case, it was part of the final stage of getting the caisson down and sealing the foundation. The deeper the structure went, the less it looked like ordinary construction. Above the river, men saw cranes, barges, forms, derricks, and concrete buckets. Below the river, a massive concrete body was pushing through mud, clay, and sand toward a bearing layer far beneath the visible world. The precision was astonishing for the tools they had. In the end, the largest positioning error recorded for the major caisson work was at Pier I, less than 1 foot east of the plan line and about 3/10 of a foot upstream. On a drawing, that looks like a correction. In the Mississippi River, after building an island, sinking a caisson, and fighting gumbo clay, it looks like a small miracle made out of labor. But not every pier could be built the same way. The Huey P. Long Bridge was not a single foundation repeated 9 times. It was a sequence of different battles along one crossing. Some piers stood in deep river conditions and needed large caissons. Others sat closer to shore or carried approach spans and could be built with different methods. Piers B, C, and D supported 3 sequential 267-foot deck spans on the eastern side. These are placed on nests of timber piles. That phrase, nest of timber piles, is worth picturing. It was not one pile under one point. It was many piles driven into the ground so that, together, they could spread and carry the load. In soft delta soils, piles work either by reaching stronger layers below or by using friction along their sides to resist movement. Timber piles have been used in places like New Orleans for generations because the city often could not trust shallow ground alone. For these piers, workers used sheet piling as a cofferdam. Sheet piles are interlocking vertical sheets driven into the ground to form a wall. Once the enclosure was in place, excavation could begin inside it. As men dug deeper, they installed bracing. That bracing was supported by temporary piles. The same pile system also supported a runway for a traveling derrick, which could move along the work and help with excavation and lifting. Inside that enclosure, a worker was not thinking about the bridge as a landmark. He was watching the wall. He was watching the brace. He was watching the place where water might find a path through the sheet piles. The whole purpose of the cofferdam was to make a small dry world inside a wet one, and every shovel of excavation made that small world deeper and more dangerous. The pattern was brutal and repetitive. Dig, brace, drive, lower, dig again, brace again. Keep the walls from pushing in. Keep the water out as much as possible. Keep the derrick moving. Keep the piles aligned. Keep the footing low enough to do its job. The excavation continued until it reached about 2 feet below the footing base elevation. Only then could the pier move toward concreting and backfill. This is the part of bridge construction most people never imagine. When they look at an old steel bridge, they see the truss. They see the towers. They see the train line, the roadway, the river view. They do not see the men in a cofferdam surrounded by wet sheet piles and bracing, working below grade while the river and the soil press from every side. They do not hear the pile hammer. They do not see the temporary runway carrying the derrick. They do not feel how much of the bridge exists only because a hidden framework was built first and then buried, drowned, or dismantled. And even the temporary work could become dangerous if the river found a weakness. During steel erection near the deck spans, workers placed a derrick on Pier V while other piles supported false work below the 267-foot spans. As they tried to erect a second derrick, the anchorage for the first one gave way. The bent supporting it had not been protected by a mattress against scour. That is the river teaching the same lesson again. A bridge is not only attacked by storms. It is attacked by ordinary moving water. Day after day, current curls around piles and bents. It removes material. It exposes support. It turns a stable point into a question. A temporary support that looks strong above the water can be undermined below it, where nobody can see the damage happening. The crew had to change the plan. The second derrick was delayed until the first was out of reach of the barges supporting its engines. That may sound like a small adjustment. On a job this large, small adjustments cost time, money, and nerve. A derrick was not a decorative machine. It was how steel members moved. It was how the work advanced. If a derrick could not be placed, the sequence changed. If the sequence changed, workers waited, barges shifted, loads moved differently, and the entire rhythm of construction had to be rewritten around the river's objection. The river objected again in 1935. While part of a 528-foot through span was being built, high water arrived. The current became too strong to install false work bents. Construction paused for more than 3 months while crews waited for the water to recede. Modern viewers sometimes imagine old builders as if they defeated nature by force alone. They did not. Sometimes they won by waiting. They watched the gauge. They watched the current. They held equipment ready. They repaired what the water damaged. They returned when the river allowed the next move. One of the 300-ton cages used to support false work tilted enough that work had to stop until the structure could be leveled and its piles red-riven after the water fell further. That image tells you almost everything about the project. 300 tons of temporary support could still be made uncertain by water and riverbed movement. So what chance did a man have if he stopped paying attention? On the Huey P. long bridge, the danger was not one single spectacular threat. It was layered. A worker handling lines on a barge had the river beside him. A pile driver crew had falling weight, splintering timber, and swinging leads. A man near a derrick had suspended loads over his head. A crew inside a cofferdam had water pressure, soil pressure, bracing, and excavation underfoot. Concrete workers had heavy forms and buckets. Iron workers later had height, wind, and open steel. And everyone had the scheduled pressure of a Depression-era job at a time when men across the country were desperate enough to write directly to politicians, engineers, and hotels asking for employment. That economic background matters, but not as decoration. It changes the human meaning of the work. These were not men building a bridge in an era of comfort. Construction contracts were executed at the end of 1932, after financing finally came together through state grants and bonds purchased by the Reconstruction Finance Corporation. America was deep in the Great Depression. Work itself had become precious. The bridge did not only move freight and trains. It put men onto barges, into cofferdams, on derricks beside pile hammers, and under steel at a time when a dangerous job could still look better than no job at all. That is one reason the best old infrastructure stories are not really about structures. They're about pressure. Economic pressure, river pressure, soil pressure, concrete pressure, time pressure, and the pressure on a crew to convert a drawing into something that could carry trains. Once the foundations and lower piers were ready, the bridge finally began to look like the thing people remember. Steel erection started from completed piers. Guy derricks lifted truss members. On some spans, a derrick moved along skids on top of stringers on the railroad floor. Moving forward, it placed truss members ahead of itself. Turning back, it placed members behind. On the way out, it built the truss and top deck. On the way back, it assembled highway, cantilever brackets, girders, and deck members. That movement is almost like watching a bridge build the track it needs in order to keep building itself. But the most dramatic steel work was the balanced cantilever method. For the main cantilever structure, workers built outward from the piers. Steel did not simply span the river all at once. Arms reached out, balanced by anchor arms and temporary support. Derrick by derrick, member by member, the structure extended over the Mississippi. The rule was balance. The anchor arm had to remain slightly heavier than the cantilever arm so that the unbalanced load could be controlled through the false work. That meant the men were not only lifting steel. They were managing a changing equation in the sky. Every new member altered weight. Every connection changed the load path. Every rivet and bolt belonged to a structure that was incomplete and therefore more vulnerable than the finished bridge would ever appear. The lower work had been about mud and water. The upper work was about height and balance. The same bridge demanded both. On one day, the problem might be a pile that had to be red-riven because water shifted the support. On another, the problem might be a derrick guide from one pier to another, holding its position while the cantilever arm grew. On another, the problem might be high water too strong for false work. On another, it might be a concrete lift 10 feet at a time, climbing above the river from a caisson that had already disappeared into the depths below. The finished bridge opened in December 1935. By then, the invisible work had done its job. Trains could cross. Road traffic could cross. The port had a fixed connection where ferries had once shouldered much of the burden. A train no longer had to treat the Mississippi as a break in the system. The river was still there, still powerful, still carrying ships and sediment. But the bridge had changed what movement through New Orleans could mean. And that is the strange thing about foundations. If they succeed, they vanish. Nobody crossing the Huey P. Long Bridge sees the willow mattresses on the riverbed. Nobody sees the man-sized stones lowered from barges to hold those mattresses down. Nobody sees the radial bends of piles that formed falsework circles. Nobody sees the steel plate rings lowered by hoist frames. Nobody sees the 35,000 cubic yards of sand used in the larger temporary islands. Nobody sees the cutting edge, the jet nozzles, the dredging wells, or the first 20 feet of concrete that began the caisson's descent. Nobody sees the 135 feet of caisson assembled before the 50-foot temporary cofferdam was added. Nobody sees the gumbo clay breaking into pieces below the water. Nobody sees the timber pile nests under the approach piers, or the sheet pile cofferdams, or the temporary pile-supported runway for the traveling derrick. They see a bridge. The work that made the bridge possible is hidden below the waterline. That is why this story fits a channel about what people built before modern machines. Because the old method was not simple. It was not primitive. It was physical intelligence under pressure. The men did not have the machines a modern crew would bring to a major river crossing. They did not have satellite positioning on every lift. They did not have digital sensors reporting every movement in real time. They did not have a computer model updating scour risk as the river changed. They had soundings, borings, triangulation, experienced engineers, foremen, divers, riggers, pile drivers, dredges, derricks, barges, and crews who knew that a foundation is only as good as the ground it reaches and the temporary work that gets it there. Modern foundation construction might use drilled shafts, advanced geotechnical instrumentation, large hydraulic cranes, GPS-controlled marine spreads, real-time monitoring, and detailed numerical models. Those tools matter. They make work more predictable, safer, and more measurable. But the Huey P. Long Bridge shows what had to happen before all of that was normal. To build one river pier, workers first armored the riverbed with a woven mattress. Then they drove piles through that mattress. Then they built a falsework circle. Then they assembled a steel shell from 10-foot rings. Then they filled it with dredged sand. Then they built a concrete caisson on top. Then they dredged inside the caisson so it would sink. Then they added more concrete. Then they sank it again. Then they fought clay. Then they sealed it. Then they built the pier shaft. Then, only then could the bridge begin a climb. That sequence is the real story. Not just the final steel. Not just the famous name. Not just the opening day train with passengers crossing for celebration. The real story is that a bridge across the Mississippi began as a fight to make mud behave. And the victory was measured in small things. A mattress landing within 15 feet of target in a 6-foot per second current. A caisson ending less than a foot offline after sinking through the riverbed. A pier shaft climbing in 10-foot increments. A crew wading out high water instead of pretending the river could be bullied. A temporary support red-riven because the river had shifted the rules. These are not glamorous details, but they're the details that kept the bridge standing. If you want to understand old construction, look for the part nobody photographs first. Look below the deck, below the masonry, below the waterline, below the mud. That is where the real labor often is. And in New Orleans, below the Huey P. Long Bridge, that labor is a story of men building islands in a river so they could sink foundations through clay to reach sand. The next time you see an old bridge pier rising from dark water, ask what had to be built before that pier appeared. Was there a mattress under it? Were piles driven around it? Did workers stand on barges loading stone while the current tried to steal their target? Did a caisson sink slowly through mud, one concrete lift at a time? Did a temporary island exist there for a few months, then vanish from memory once the bridge took over the skyline? That is the hidden world of these structures. And it is why the Huey P. Long Bridge was not just built across the Mississippi. It was built into it. The river was the obstacle. The mud was the trap. The sand far below was the prize. And the men in between had to turn water, timber, stone, steel, and concrete into a foundation strong enough to carry a city across. So here's the question. If a modern bridge can hide this much work below the water, how many other old structures are standing on stories we never see? Tell me the oldest bridge, pier, dam, tunnel, or waterfront structure near your city that looks simple from the surface, but probably has a brutal foundation story underneath it. Because the most impressive part of an old machine-age structure is often not the part above your head. It is the part buried under your feet.